All right, good afternoon. Here we are again for another lovely session of ENGR 2302 Engineering Dynamics. This will be the 16th lecture in the series, and today we're going to continue on with some more examples on the previous topic, which of course are energy methods for rigid bodies and systems of rigid bodies. And then we'll be moving on to some new material, including momentum considerations, impulse momentum, etc., for rigid body systems. So let us begin. All right, so consider two gears here. I'm going to have a system consisting of two gears. So that's going to be my first example for today. Consider two gears of different diameters. So I'm going to have two gears of different diameters. And I'll be lazy and just draw these gears as a couple wheels or a couple circles. So, but these are two gears that are joined by teeth that will make sure they don't slip. So I have wheel A here, and then I have wheel B. Wheel A and wheel B. And then let me draw the diameters on here. Wheel A will have a radius, I should say, of 250 millimeters. And wheel B will have a radius of 100 millimeters. And wheel B will have a radius of 100 millimeters. And then I'll be given the K, and what is K again?
The radius of gyration.
Good, the radius of gyration. So I'm told the following information. I am told that MA, the mass of A, is going to be 10 kilograms. And the KA, the radius of gyration of A, although different books may use different labels, is going to be 200 millimeters. And MB, the mass of B, is going to be 3 kilograms. And the radius of gyration, wow, okay. The radius of gyration of B is going to be 80 millimeters. Don't mind me, I'm just clearly drunk. All right, let us consider this. And then we'll also be told that the system is at rest when a moment, or when a couple of, that sounds like I'm talking about two objects, when a moment of, let us say, 6 Newton meters is applied to B. To gear B. Again, I drew these as wheels, as simple discs, but in reality, these are gears. I just didn't feel like drawing a bunch of teeth. Okay, so we're going to neglect friction, and then find, also, we are told that this is frictionless. And so all of this is given, and then find, let's say, A, the revolutions required. The revolutions required of gear B before its angular velocity reaches 600 RPM, omega, its angular velocity omega reaches 600 RPM. And B, I also want to find the tangential force The tangential force exerted on a B by A. Exerted on gear A by gear B. And this is actually very important to this type of design, this type of consideration is very important to many types of mechanical systems. So, you know, when you are a child or when you're a high school student or whenever, maybe even a child, it can experiment with some of these principles where, did anyone ever experiment with like mechanical advantage or, you know, gear systems when you're a kid where you have, you know, maybe some sort of toy that lets you join different types of gears together and you can see that if you connect one set of gears to another with a pulley or with another axle, you can get higher and higher and higher gear ratios until you'll eventually, you know, you turn one crank one time, and the other gear wants to turn 10,000 times or something like that, right? Well, you know, as a kid, you always wonder, well, what's the limit of this? How far can I take this? And there's a couple limits. One is, of course, friction. A very fast-spinning pulley or a very fast-spinning gear will have high amounts of friction. But the other is actually this force here, this tangential force. Yes, you can make one gear turn very fast or exert a great amount of force in the form of mechanical advantage if you wish. But the downside is those gears must be able to take that force. In other words, if you have a tooth gear type thing like this, a surface like this, and the other one coming in like this to meet it, well, this is just one metal surface bearing against another metal surface. And the forces here will want to cause one set of teeth to shear the other set of teeth off. And if you're not careful, when you're actually when you're working with systems in physics, you're going to assume that the materials are, you know, non-deforming, that they're rigid bodies, that they can effectively take infinite force. But in reality, all real systems can't do that. So if you're actually designing an engine that is transmitting large amounts of power via gearing, then this becomes one of your primary design considerations. Just making sure that the forces and in turn the stresses in your gears does not exceed an allowable value. Okay, so let us consider this here. Okay, so I want to start by evaluating the final kinetic energy of the system. I'm going to do this through the use of energy rather than the use of impulse and momentum right away. So consider the two gears. And I'm going to use two different labels. I'm going to say we have two different omegas. We're going to have omega B going like this. And I'm just going to go ahead and assume omega B is clockwise because it was given to me as a clockwise, I'm going to assume omega B is counterclockwise because it was given to me as a positive number, but really it doesn't matter. And then omega A would go like this. Omega A would be like this here. Okay, so let's find this. And bit of note, these are two gears that are joining together. Now, let's think about this. Let's think in terms of gears. Will their angular velocities be the same? No, their angular velocities will not be the same. But what will be the same? What will be the same? At their point of intersection, their tangential velocities will be the same. That's what's going to be the same. These are two surfaces, and I didn't draw them right on top of each other, but as we can see here, these are two surfaces that are physically not going to slip past each other. They're not bearing on via friction or something like that. What's going to keep them rotating together is their teeth, not bearing friction. I just didn't feel like drawing them like full gears. But in reality, they have teeth that are intersecting and preventing them from slipping past. So this plane must move with this plane here. So they're going to have the same tangential velocity. They're not going to have the same angular velocity, but they will have the same tangential velocity. It's just like if I had if I connected one wheel within another wheel. You know, I have say a drum and a spindle inside, or a drum connected to a big wheel or something like that, like we've seen previously. In this type of a system, they don't have the same tangential velocity, but this whole thing both of the joined systems do have the same angular velocity. So spinning objects, depending on how they're connected, can either have the same angular velocity, the same tangential velocity, or neither or both. Okay, so anyway, whenever you have two things joined together at a shared surface, or a shared outer surface, they're going to have the same tangential velocity. So my first step will be, well, I need to first find the, I want to first find the angular velocities of each.
So if they were speeding up or slowing down, they'd have the same tangential acceleration as well.
Yes, exactly. If they were speeding up or slowing down, they would have, and they are in fact actually speeding up or slowing down, because we're going to be looking at an initial and a final. It started from rest, and then I'm saying basically, the revolutions required of B before omega reaches 600 RPM. So it actually is accelerating, yes. But in the same case, yes, if they're accelerating, they will have not only the same tangential velocity, but the same tangential acceleration. They have to be in contact. So omega B then is going to equal, I want to find omega B, and I'm just going to use the knowledge that this is 600 RPM. I'm just going to convert RPM to radians per second times 2 pi radians per revolution, and then 60 seconds divided by minute, 60 seconds per minute, and then that produces a value of 62.8 radians per second. 62.8 radians per second. So I calculated my angular velocity at B. Next, I want to calculate my angular velocity at A. And this is just going to be based on the relationship. Well, I want to elaborate. What I have is, I have this equation written down, but I would actually like to develop that a little bit, where I know that omega A equals RB over RA. But I would actually maybe like to develop that a bit more, because I don't just want to times omega B. This is what I have in my notes. But I would like to maybe develop that. So where did this come from? Well, this came from saying, well, velocity, not angular velocity, but just velocity of A is equal to velocity of B at this point of contact. So, and I know that linear velocity is going to be equal to omega times R. So omega A times RA equals omega B times RB. And from this, I can get that omega A equals omega B times RB over RA. Times RB over RA. Like so. Okay, so omega B times RB over RA, but that's just a small development up to the side. And then this is going to be, let's say 62.8, the value I had previously. 62.8 radians per second times 0.100 so this is the radius in meters, divided by 0.250. We'll just divide it by 0.250, and this is equal to 25.1 radians per second. Radians per second. Next, I want to find the moment of inertia of each of these things. So I bar A, or IA, is going to equal MA. Let me leave the bar off. I think it's kind of obvious that we're talking about the centroid, which is about the center of rotation at this point in this system. And this is, so IA is going to be equal to MA times KA squared. So the moment of inertia is equal to the mass times the radius of gyration squared, which is 10 kilograms times 0.200 meters squared, or 0.40 kilogram meter squared. Kilogram meter squared. And IB then is equal to MB KB squared, or in other words, the moment of inertia of B is equal to the mass of B times the radius of gyration of B squared, and that will be equal to 3 kilograms times 0.080 meters, quantity squared, which is equal to 0.0192 kilogram meter squared. Kilogram meters squared. All right, and then I want to find the total energy at 2. Okay, so I want to find the total energy at 2, or sorry, not the total energy, the kinetic energy at 2. T2 I want to find the kinetic energy at 2 and say that okay, my basic principle here, the reason I'm trying to go for the kinetic energy is that I know that I'll be able to I'll basically be able to say, well, previously we've looked at the amount of work that is required that a moment will do over a change in angle, right? And so I'm looking for that change of angle. So if I can know, I know that there's no gravitational potential energy really going on here. So I know that if I can find the kinetic energy at point 2, which is the point where the thing is rotating at 600 revolutions per minute, I will know, if I can find the total energy there, I can find the distance and angle, the change in angle required to produce that. So T2, the total kinetic energy at point 2, at time 2, is 1/2 IA times omega A squared plus 1/2 IB times omega B squared. And then this is then equal to 1/2 times 0.400 kilogram meter squared times 25.1 quantity squared plus 1/2 times our 0.0192 times our 62.8 radians per second. All of this quantity squared, and I get that the total kinetic energy at point 2 is 163.9 joules. So the total kinetic energy after this period of acceleration is 163.9 joules. Or 163.9 joules. Next, I want to apply the equation of work and energy. Apply work energy principle. And this, of course, states that T1 plus U from 1 to 2 is equal to T2. So our initial kinetic energy plus all the work put in from 1 to 2 is going to equal the kinetic energy at point 2. And this is going to be 0 plus the work from 1 to 2 will simply be, let us say, well, I know that 6 Newton meters are being applied to this thing. I know that so I know again that U from 1 to 2 is going to be equal to M delta theta, and we remember that from the previous class. And so this is going to be then, or I could simply say that, let's see here. The M is going to be, I know my M is equal to 6 Newton meters, or 6 joules. That the Newton meters is obviously the same unit as joules. So if I put in, so I know this is again M delta theta equals T2. And so then I can say, well, M is 6 Newton meters times delta theta will be equal to our T2, which of course again is 163.9 joules, times delta theta, and delta theta is going to be 163.9 joules divided by 6 Newton meters, which will come to 27.32 radians. Or I can convert that to revolutions. And since we were given it originally in revolutions, we can just go ahead and use that, because actually, I shouldn't just assume that it's okay. I actually do have to convert it to revolutions because it's asking for revolutions. So 27.32 radians times 1 revolution divided by 2 pi radians. And I find that I need 4.35 revolutions, and that would be my first final answer. My first final answer. It's an interesting phrase. The final answer to part 1. So this whole thing is going to have, in order to get up to an angular velocity of 62.8 radians per second, we're going to need to rotate through 4.35 revolutions. Okay. Now let's see. I next wish to find the force between the gears. The force between the gears. To do this, I will apply work and energy just to gear A. I will apply work and energy just to gear A by itself. By itself. Gear A by itself. And basically, I'm going to apply this, and then once I have this energy required, I will then, since I know the work, I will find the torque needed, and from this, the force needed. And thus the force needed. And thus the force needed. So, moment and tangential force required for the indicated work. Okay. So I know that the change in angle, delta theta, or the delta theta of A is going to be equal to delta theta B, or I could just say theta A, that should be fine. Theta A, theta B is going to be equal to RB over RA. And where this would come from is not from setting the tangential velocities equal to each other. This would come from setting the tangential displacements equal to each other. In fact, again, let me do that. Let me actually do that in this case. Instead of just writing it, let me do that, because I know that the arc length traveled by each of them, the distance traveled by each of them, so it will be the same at that point, or because they meet up and join at that one point. So I know SA is equal to SB. SA would be the linear distance traveled by a particle on the wheel, or the distance traveled by a particle on the wheel as it rotates around multiple revolutions. And I also know that S is equal to R theta, is it not? So so basically, RA theta A would be equal to RB theta B. And so therefore, theta A is going to be equal to theta B times RB over RA. RB over RA, and then this equals 27.32 times 0.100, so 0.100 divided by 0.250, and this will then be equal to 126.0 joules. 126.0 joules. Oh, that's not right, sorry. They're getting ahead of myself. This is equal to 10.93 radians. So thus, even though these have the same linear velocity, these are ultimately going to have very different angular velocities and different angles traveled. So this is saying that while B is going to travel 27.32 radians, A is only going to travel 10.39 radians, and since it's much larger, that makes sense. Then I want to find I'll need to find the kinetic energy at point 2 of just A. Kinetic energy at point 2 is 1/2 IA omega A squared, and this is 1/2 times 0.400 times 0.400 times 25.1 quantity squared. And this is equal to 126.0 joules. 126.0 joules. So fairly straightforward. That is, now, again, why am I only including the kinetic energy of one of the gears here? Did I make a mistake? Is that a typo? No. If you notice, I will apply work and energy to just gear A by itself. So we observe from this problem that we don't need to construct things for the entire system. You can look at these in terms of the entire system. You can look at these in terms of just an individual piece. In fact, if you really wanted to, although it wouldn't be the wisest thing to do, you could actually, I could analyze work and energy in this problem for a single gear, for a single gear tooth. If I knew enough about the system, I could do that. Now, we'd have to really get into the details of what material it's made of and how the forces distribute through it, but you could actually work through that just from one tiny bit of matter there. But anyway, 126 joules. So I know the kinetic energy at point 2 of object A, of gear A. Finally, I'm going to apply the principle of work and energy. I will say that T1 plus U from 1 to 2 is equal to T2. And this again is just for gear A. So gear A's kinetic energy initial plus the work done on it from 1 to 2 will equal the final kinetic energy. And so then I can say that, T1, this is 0. It starts from what? It starts from rest. Plus MA times 10.93 radians. Again, the work done by a couple or by a moment will be m d theta, or m theta. And this equals 126.0 joules. The 126.0 joules we had previously. And then finally, I can get that MA by dividing, so MA is going to be equal to 126 joules divided by 10.93 radians, which will equal 11.52 Newton meters. Then I can say that, okay, well look, this moment is ultimately caused by a force. So I have this force here. First I have RA. And I have a force, this unknown F that I'm solving for. If remember, my final thing that I'm looking for is a force here, and then this will be producing some sort of moment M. And that's what this M here is. And then I can say, well, MA is equal to RA times that F, or F equals MA over RA, or capital MA, divided by RA, equals then, that's going to be 11.52 Newton meters, divided by 0.250 meters. Uh, 0.250 meters, is that right? Yes, 2.0 meters. And I get, when this is all done, that force is equal to 46.2 newtons. .2 newtons. So, morals here, lessons. One can do energy balance on whole system or individual pieces. Or individual pieces. And what else? Let's see. And can relate gears by tangential velocity. By tangential velocity. Yes.
I understand the T1 plus U1 to 2 equals T2. Then how come the moment of A and the angle of A, why do you have to use that there?
Why do I have to use the moment of A?
And the 10.3
Okay, the whole idea here is that I know that why am I doing? In other words, why am I doing this? Well, I know that the work from 1 to 2, because this thing starts out at no kinetic energy. I know that it starts off with 0 energy, basically, right? Because it's not initially it's at rest. It's not falling from a great height or something. So it's initially at 0 energy. Now, the just a second, I'm having some. Come on, you. Having a little technical difficulties here. Let's see, is this working? Okay, yeah. Okay, we're good. Okay, now I'm back. Sorry about that. So I know that the kinetic energy here, this kinetic energy has to come from somewhere, right? And it's coming from the work. The work I'm inputting into gear A is where this energy is coming from. Does that make sense? This represents the kinetic energy of gear A at the end, and that energy has to come from somewhere, and it comes from it comes from the from 1 to 2 term. That is the work energy that's being inputted into gear A by an outside source. Make sense? Okay, good. Then that work is going to be equal to the U from 1 to 2 is going to be equal to m d theta. The mass, the moment times the change in angle, the rotation angle. Does that make sense then? Okay. Any other question? I mean, are you sure that makes sense? Okay. All right. Let's see here. Okay, maybe we'll work through another example. I like these examples, they're kind of nice. Okay, so let's say we have this, example 2. A sphere, this is kind of a classic physics problem. A cylinder and hoop, each with mass m, and radius r, are released on an incline from rest. Are released on an incline. Determine the change in velocity each experiences, or the increase in velocity. And they're all released from rest. For each of them, as they drop to their distance corresponding to h. At distance h, some distance h. Alright, so let us begin. Okay. Let's see. So what I can say though is the for each of these, since m is constant, gravity will apply the same work to all of them. And then they're going to have the same work to all of them. However, they will not have the same, or they'll have the same total kinetic energy, but not quite. So, well, actually, yeah, they will have the same kinetic energy. So again, therefore, they will all have the same final kinetic energy. They'll have the same final kinetic energy. Then, let's see. I know omega equals v over r. Omega equals v over r. And then plugging in terms to the energy equation, I can say T2 plus T2 is equal to 1/2 mv squared plus 1/2 I omega 2 squared, or just omega squared, 1/2 I omega squared, and this is then equal to 1/2 mv squared plus 1/2 I times v over r quantity squared. V over r quantity squared. Or T2 is just equal to 1/2 times m, let's see, plus I over r squared. I over r squared v squared. So that's the final kinetic energy as a that's just the final kinetic energy. All right. Then I can say that T1, again, and then plus u from 1 to 2 is equal to T2. And the initial kinetic energy is 0, but 0 plus WH is equal to 1/2, and that is weight times height, WH, times m plus I over r squared. I over r squared. Here, yeah, m over r squared, and then times v squared. So again, I'm just replacing various terms with each other, and what this is basically, this is essentially coming down to is, actually I got a little ahead of myself, sorry, no, actually I guess we're good, never mind. V over r squared, and T2 is equal to this, I over r squared v squared, and again I have this, just replacing, basically all I did was I replaced u1 with w times h, the weight times the height, because really that's the work that's going to be done. It's the work that will be done on the block, on the object, is simply from gravity. That is the weight times the height. And then, let's see, solving for v squared, I can get that v squared equals 2wh divided by m plus I over r quantity squared, I over r quantity squared, equals 2gh divided by 1 plus I over mr squared. Divided by 1 plus m over r squared, yeah, m over r, or just, actually that's not right, not I m squared, I over mr squared, sorry about that. I over mr squared. And then I have this piece of information here now, so I know that I really basically have my equation in my final form. I can say that v is equal to the square root of 2gh over I plus, or 1 plus I over mr squared. I over mr squared I over mr squared all right, and now all I need to do is find the i's of each of these and plug them in. So for a sphere, well, I'll just do this on a couple slides. For the sphere, the formula is I equals 2/5 mr squared. 2/5 mr squared. And this will come to 0.845 square root of GH. And then for a let's see, so a cylinder, I equals, oh wait, that's not quite right, 2/5 mr squared, but then V is equal to 0.845 square root of GH, or square root of 2GH. Man, I'm making all sorts of typos today, sorry about that. In the case of the sphere, the V is going to equal to 0.845 times the square root of 2GH. For the cylinder, the I is 1/2 mr squared, which plugging and chugging equals V yields V equals 0.816 times the square root of 2GH, square root of 2GH. And then for the hoop, I can say, again, for this one, it's going to just be I equals mr squared for the equation of moment of inertia. And then V equals 0.707 square root of 2GH. So again, this one is 0.707, this is 0.816, this is 0.845. So the highest case will actually be the sphere and the lowest the hoop. All right, and that is the basic relationship. So in other words, because this has a faster velocity at time 2, it will have a higher velocity, or sorry, it'll have a because it has a lower inertia, it will have a higher velocity, and that makes sense if you think about it. All right, I think I'm gonna take a break there, cut it there, and we'll come back and look at some new material. All right, thank you.